In basic principles of design of experiment, we already discussed three basic principles, that is randomization, replication and local control. In this module, we use the concept of blocking or local control in using with CRD, that is completely randomized design. Let's get started. We will discuss about the second most widely used design to solve practical problem. This design is called randomized block design. The construction of the RBD, that is mathematical derivation, as well as its statistical analysis will be discussed. Some other aspect will also be discussed in brief. We will also discuss briefly about the random treatment and blocks. We will also discuss another important design which is called the Latin scale design. Latin scale design is used in those situations where we have two nuisance factors. In this module, introduction to the design and its mathematical derivation will be discussed. A few brief introduction about the application of the Latin scale design will be discussed. This design is an extension over the CRD design where the effect of nuisance factor need to be controlled. Nuisance factor is that factor which has an effect on the response variable in an indirect manner. It is possible that this nuisance factor cannot be determined and uncontrollable, but we just have the information about the existence of this factor. As we already discussed about the three principles of experimental design, these are randomization, replication and local control. Randomization is used to remove the effect that occurs due to nuisance factor. It is also possible that we have some information about the nuisance factor and it can be controllable. In this situation, we have to introduce the concept of blocking or local control in our model. It is basically used to eliminate the effect of nuisance factor while the testing of treatment means. Hence, due to involvement of the blocking term as well as randomization in the model, the design is named as randomized block design. While building the model for the observation, we want to keep the experimental error term to be small as possible, as we are more interested in removing the variability that arise due to the effect of experimental error. Hence, the randomized block design helps the experimenter to take care of this variation. Suppose the experimental area is heterogeneous and we want to control the variability of the experimental material with respect to effect of randomization in one direction. Randomized block design is used to control the variability of the experimental material. Data divided into groups into homogeneous subgroups or strata of blocks perpendicular to the effect that arise in the experimental units. Hence, the main purpose for blocking is to provide same platform to the treatments so that one can test the treatment mean in more appropriate manner and the variation that appears in the treatment value on the experimental units are not influenced by any external factor, rather they only arise from the variation in the features of the treatments. Now we will discuss what is randomized block design. In randomized block design, treatments are randomly applied to the homogeneous units within each block and replicate over all the blocks. In this module, we discuss about the model of the RBD. In literature, one can read about how to estimate the parameter of the model and what are the methods that are available in the literature for estimation. While estimation, it is also essential to take account of some condition. In practical life, there are situations when data from some individual units are missing. To solve this type of problem, the missing plot technique is used. One can refer to the literature for in-depth study of RBD. Nowadays, statistical softwares like SPSS and programming language like R, Python are used to do the analysis part of the experimental design like CRD, RBD and Latin scale design, etc. Suppose we have P treatments that are to be compared within Q blocks. The structure of the RBDs will be given in table number 1. So in the first column we have treatment with us So we have P treatment with us, and in the first row we have Q blocks. So first observation, that is YY1 denotes the first treatment within the first block, and Y21 represent observation of the second treatment in first block, and so on. Similarly, we can see that there is only one observation per treatment in each block, and order in which treatment are allocated to the experimental units are defined randomly within each block. There is only one randomization in within blocks. The statistical model for RBD effect model is given as Yij is equal to mu plus tau I plus beta j plus epsilon ij, where I vary from 1 to p and j vary from 1 to q, where and mu represents the overall mean and tau I is the ith treatment effect. Beta j denotes the jth block effect, and epsilon ij random error effect, and where epsilon ij follow normal distribution with normally identically distributed random variable that with parameter 0 and variance sigma square. Generally, treatment and blocks are fixed factors, so that treatment and block effect as deviation from the overall mean is given as summation over tau I, where I vary from 1 to p is equal to 0, and summation over beta, and where summation is over j and j vary from 1 to q is equal to 0. The effect model will be known as mean model by treatment of this, that is mu ij is equal to mu plus tau I plus beta j. The objective of the RBD is to test the equality of the treatment mean. Thus the hypotheses are given as H0, which is equal to mu1 is equal to mu2 is equal to mu p, and alternative is at least one mu I is not equal to mu j. Since ith treatment mean is equal to mu I, which is equal to 1 upon q, and into summation mu plus tau I plus beta j, where summation is over j, where j vary from 1 to q, and which is equal to mu plus tau I. Then the other alternative hypotheses are H0. We are testing here tau i's, whether tau i's are significantly 0 or not. So we have null hypothesis as tau 1 is equal to tau 2 is equal to tau p is equal to 0, and alternative hypothesis given here as at least one tau I is not equal to 0. So average of the observation with respect to the ith treatment, that is mean, is equal to total of observation under ith treatment divided by number of treatments. So yi dot bar, which is equal to yi dot divided by q, and y I dot bar, which is equal to summation is over yi j, and summation is over j, and j vary from 1 to q divided by q. So average of the observation with respect to jth block, that is y dot j bar, which is equal to summation yij, and summation is over I, where I vary from 1 to p divided by p. The grand average of all the observations are given here as y double dot bar, which is equal to double summation yij, where summation is over I and j, where I vary from 1 to p and j vary from 1 to q divided by p q. The total sum of square is represented as double summation yij minus y double dot bar whole square, where summation is over I and j, where I vary from 1 to p and j vary from 1 to q. And by after put adding the term y I dot and y dot j, we have the expression as given here as y I dot bar minus y double dot bar plus y dot j bar minus y double dot bar plus yij minus yi dot bar minus y dot j bar plus y double dot bar whole square. By expanding this equation, we get the following equation as double summation yij minus y double dot bar whole square, which is equal to q times into yi dot bar minus y double dot bar whole square, and summation is over I, where I vary from 1 to p, plus p times y dot j bar minus y double dot bar whole square, and where summation is over j and j vary from 1 to q, plus double summation yij minus y I dot bar minus y dot j bar plus y double dot bar whole square, where summation is over I and j, and I vary from 1 to p and j vary from 1 to q. This equation is represented as a partition of the total sum of square, In this partition, first term represents treatment sum of square, second term represents block sum of square, and last or third term represent the error sum of square. So we can write total sum of square is equal to sum of square due to treatment plus sum of square of blocks and sum of square of error. Since we have total observation capital N is equal to PQ, the degree of freedom of the total sum of square is equal to N minus 1. The total number of observations are P, so that degree of freedom of the treatment sum of square is P minus 1. The total number of the blocks are Q, so that the degree of the freedom of the block sum of square is Q minus 1. The degree of freedom of the error sum of square is given here as sum of square of error degree of freedom, which is equal to sum of square of total degree of freedom minus sum of square of treatment degree of freedom minus sum of square of block degree of freedom. So sum of square of error degree of freedom, which is equal to PQ minus 1 minus P plus 1 minus Q plus 1, which is coming out to be P minus 1 into Q minus 1. So mean sum of square is also a part of the ANOVA table. Mean square is the ratio of the sum of square to the degree of freedom. That is, mean sum of square is equal to sum of the square divided by degree of freedom, and mean sum of square to the treatment, which is equal to sum of square of treatment divided by P minus 1, and mean sum of square to the block, which is equal to sum of square of block divided by Q minus 1. So mean sum of square to the error, which is equal to sum of square of error divided by P minus 1 into Q minus 1. The total the test statistics to the test the equality of treatment, which is equal to F naught, which is equal to mean sum of square of treatment divided by mean sum of square error. The test statistics follow F distribution P minus 1 and P minus 1 Q minus 1 degree of freedom. That is F P minus 1 P minus 1 and Q minus 1. If F naught is less than F P minus 1 comma P minus 1 into Q minus 1, the null hypothesis for the testing of treatment mean is not rejected. Otherwise, F naught is greater than F P minus 1 P minus 1 Q minus 1, then reject the null hypothesis. The analysis of the variance table for the RBD is given here as, in the first column we have source of variation, that in which we have treatments, blocks, errors and totals, and in the second column we have sum of square, in which we have sum of square due to treatment, sum of square due to blocks, sum of square due to error, and at last we have sum of square due to total. So we have degree of freedom corresponding to sum of square treatment as given as P minus 1, sum of degree of freedom for blocks is given as Q minus 1, and some degree of freedom for error term is P minus 1 Q minus 1, and degree of freedom for total is given as N minus 1. So mean sum of square is derived as sum of square of treatment divided by degree of freedom, that is sum of square of treatment divided by P minus 1, and mean sum of square of block, which is equal to sum of square of blocks divided by Q minus 1, and sum of square mean sum of square of error, which is equal to sum of square of error divided by P minus 1 into Q minus 1, which is equal to mean sum of square of error. And F statistics can be derived as proportion of sum of square of treatment divided by sum of square of error. So if we are interested in to test the equality of the blocks, that there is no significant difference between the beta j's, then the F statistics can be evaluated as mean sum of square of blocks divided by mean sum of square of error. From table 2 we see that the last column will give you the F statistics value. This F statistics value is used to draw conclusion about the null hypothesis. One can also test for the equality of the blocks by making statement about the null hypothesis and evaluate F statistics for the blocks. After comparing the calculated F statistics value with the tabulated value, one can make a decision about the equality of the blocks. So there are other aspects of the randomized block design. There are situations when increment in the expected response variable by few units due to any treatment or due to any block, then how to take care of this increment in the model. In general theory, it is considered that in RBD the principle of additive theory is used, as we have already defined the RBD model as the sum of mean effect, block effect, treatment effect and error term. Hence, it is assumed that if treatments or block increase the value of the response variable in units, then the incremental value will be reflected in the total value, but this is not considered as a relevant situation in general. The reason behind this is that if change occurred due to any treatment or block in response variable, then there is a change of interaction that occur between treatment and blocks, so there is need to incorporate interaction term in the model. but it is not recommended to use interaction term as it inflates the residual mean square that adversely influence the treatment mean comparison. To tackle this problem, we have to use another design like factorial design. Randomized treatment and blocks. The design that we discussed in the previous section consider both the treatment and block as a fixed factor. There are many situations where both the treatment and blocks are random. In most of the situations, blocks are considered to be random quantity. It will be beneficial for the experimenter to check the validity of the experiment across the random sample of the block. Now we will discuss another model, that is Latin scale design. Latin scale design is basically an extension of the randomized block design. Latin scale design is another design that utilizes the principle of blocking. It is possible that in the experimentation of the system we have more than one nuisance factor. If we have only two nuisance factors, then the design that consists of taking account of these factors is called Latin scale design. The most important feature of Latin scale design is that it is in square arrangement and usually denoted by the Latin letters. Hence, the design is named after the Latin letter. The main purpose of the Latin scale design is to remove the variability that arises from two nuisance factors. In Latin scale design, we implement the principle of blocking in two directions. Hence, rows and columns are generally considered as the two-way factors that restrict the implementation of randomization. In the testing of the treatment mean, in this we have p-square cell and treatment are represented in each cell with Latin letters, and each letters occur one and only one time in each column and rows. The statistical model for LST effect model is given as Yij is equal to mu plus alpha I plus tau j plus beta k plus epsilon ijk, where I vary from 1 to p and j from 1 to p and k vary from 1 to p, where mu represents the overall mean, alpha is the ith row effect, tau j is the jth treatment effect, beta k is the kth column effect, and epsilon ijk represents the error term that follow normal distributed random variable and that with mean 0 and variance sigma square. We can see that the effect model of LST is completely additive model, so that there is no interaction effect between rows, columns and treatments. One more reason for the no interaction effect between rows, treatment and column, that is there is only one observation each cell for the LST layout. Average of the observation with respect to jth treatment, that is mean is equal to total of observations taken under jth treatment divided by number of treatments. So y dot j dot bar, which is equal to y dot j dot divided by p, and y dot j dot bar, which is equal to summation is over j and yijk divided by p. So average of the observation with respect to kth block, that is y double dot k bar, which is equal to y dot dot k upon p, and y dot dot k bar, which is equal to summation is over k yijk divided by p. The grand average of all the observation, which is equal to yij, and summation is over yij, and where I vary from 1 to p, j vary from 1 to p and k vary from 1 to p, divided by p square. The total sum of square represent as triple summation ijk and yijk minus y triple dot bar whole square, which is equal to triple summation yi double dot bar minus y triple dot bar plus y dot j dot bar minus y triple dot bar plus y double dot k bar minus y triple dot bar plus yijk minus yi double dot bar minus y dot j dot bar minus y double dot k bar plus y triple dot bar bracket whole square. So by expanding this equation, we get the equation as triple summation yijk minus y triple dot bar whole square, which is equal to p times summation is over yi dot bar minus y triple dot bar square plus p times summation y dot j dot bar minus y triple dot bar whole square, where summation is over j and j vary from 1 to p plus p times the expression y double dot k bar minus y triple dot bar whole square, and summation is over k and k vary from 1 to p, and plus triple summation yijk minus yi double dot bar minus y dot j dot bar minus y double dot k bar plus y triple dot bar whole square. The NOVA for the LSD consists partition of the total sum of square into the row component, column component, treatment component and error component. This is given as sum of square of total, which is equal to sum of square of row plus sum of square of treatment plus sum of square of column plus sum of square of error. Since we have total observation which is equal to n is equal to p square, the degree of freedom of the total sum of square is equal to p square minus 1. The degree of freedom is p minus 1. Same for the treatment sum of square, also for the rows and row sum of square and column sum of square. The degree of freedom of the error term is given as sum of square of error degree of freedom, which is equal to sum of square of total degree of freedom minus sum of square of treatment degree of freedom minus sum of square of log degree of freedom minus sum of square of rows degree of freedom. Error degree of freedom, which is equal to p square minus 1 minus p plus 1 minus p plus 1 minus p plus 1. After solving, if we get the sum of square of error degree of freedom, which is coming out to be p minus 1 and into p minus 2. So mean sum of square to the treatment, mean sum of square of row, which is equal to sum of square of row divided by p minus 1. Mean sum of square to the treatment, which is equal to mean sum of square of treatment, which is equal to sum of square of treatment divided by p minus 1. Mean sum of square to the block, which is equal to sum of square of column divided by p minus 1. And mean sum of square to the error, which is sum of square of error divided by p minus 1 into p minus 2. The test statistics to test the equality of the treatment mean is f naught, which is equal to mean sum of square treatment divided by mean sum of square error. Test statistics follow f distribution p minus 1 and p minus 1 p minus 2 degree of freedom, that is f with p minus 1 p minus 1 p minus 2. If calculated value of f is less than the tabulated value, that is f with degree of freedom p minus 1 p minus 1 p minus 2 at alpha level of significance, then we conclude that we do not reject the null hypothesis. And if the calculated value of f is greater than f naught which is greater than f with p minus 1 and p minus 1 into p minus 2 degree of freedom at alpha level of significance, then we reject the null hypothesis. The analysis of the variance table for the LSD is given here as: in the first column we have source of variation, and in the first row we have treatment, in the second row we have rows, in third column we have blocks, and in the fourth row we have blocks, in the fifth row we have error terms, and the last we have totals. So in the second column we have sum of square of treatment, sum of square blocks, sum of square of errors, and sum of square of total, and degree of freedom is given in the column number 3, and mean sum of square is evaluated in column number 4, and f statistics is evaluated in the column number 5. So in table 3, the last column test statistics value will help you to make a decision about the null hypothesis. We can also test about the equality of row and column using the testing of hypothesis. In that case, we have to evaluate the test statistics f for each case respectively and compare the test statistics value with the tabulated value to make a conclusive statement about the equality of row and column. So in the next section we will discuss some examples of RBD and the Latin scale design. So a scientist wishes to test the effect of 3 research projects in the strength of a particular type of cloth. Because there might be variability from one bolt to another, the scientist decided to use a randomized block design with the bolt of cloth considered as block. She selects 4 bolts and applies all 3 research projects in random order to each bolt, analyze the data for this experiment at 5% level of significance, and draw appropriate conclusion. So from the table we have research project is given in the rows 1, 2 and 3, and bold represent the columns 1, 2 and 3, 4. Randomized block design for the research project is is given here in the table number 5. So the total sum of square by applying the formula that is given in the theory part. So after putting the value in the formula, we get the result as sum of square of total, which is coming out to be 1862.25, and the treatment sum of square value can be derived by putting the value in the formula. We get the result as 703.5. So similarly, the block sum of square is evaluated as by putting the value in the formula, that is 1106.91. Now to find out the error sum of square, we can do is what we can do, we can subtract treatment sum of square and sum of square of block from sum of square of total. We will get the value as 1862.25 minus 703.5 minus 1106.91, which is coming out to be 51.84. Mean sum of square to the treatment, which is equal to sum of square of treatment divided by degree of freedom, that is p minus 1, and sum of square of mean sum of square of treatment, which is equal to 351.75. Mean sum of square to the block can be found by using the same formula. So we get the result as 368.97, and mean sum of square to the error term, which is coming out to be 51.84 divided by 6, which so answer is 8.64. The test is 6 to test the equalities of treatment mean. So f naught here is mean sum of square of treatment divided by mean sum of square of error, so which is 351.75 divided by 8.64, so which is equal to 40.711. The f statistic tabulatory value at 5% level of significance with 2 and 3 degree of freedom is can be seen from table, which is coming out to be 9.55. The analysis of the variance table for the RBD, from the table we can see that the calculated value of f is given here as 40.711, and the tabulatory value of f is 9.55. So that we can say that there is a significant difference in the mean values of all the treatment. The three research projects differ in terms of the strength of cloth. Hence, the strength of the cloth of research project differs in different blocks. So in the second example, we have a manufacturer that wants to study the effect of the 6 different formulation to manufacture the part of the swing machine. Each formulation mixed from a batch of raw material that is only one large enough for 6 formulation to be tested. The formulation of the part of the swing machine are prepared by several operators. Thus, if it would seem that there are 2 nuisance factors to be controlled, that are batch of raw material and operators. So in the first column we have batches of raw material, and in the next columns we have operators, and we have 6 rows that represent the batches of raw material, and we have 6 operators also. The design that will be appropriate for this problem is Latin scale design. LSD is a square arrangement design, and 6 formulation represented by the Latin letters A, B, C, D, E and F. We can see that table is 6 cross 6 table. So after coding the above table by subtracting 6, the new table is given here. The total sum of square, which is equal to triple summation yij square minus y triple dot square upon n. So the sum of square of total, which is coming out to be 67.24. The row sum of square can be derived by same formula, and the sum of square of batches, which is coming out to be 3.83. and the column sum of square, that is sum of square of operator, after putting the value in the formula we get the result as 12.70, and the treatment sum of square, which is equal to 1 upon p summation y dot j dot square upon minus y triple dot square upon n. So sum of square of formulation, by putting the value in the formula we get the result as 1.44. So the solution is given here in the table number 9. So the error sum of square is derived by subtracting sum of square of treatment minus sum of square of blocks and sum of square of rows from the sum of square of total. So we get the sum of square of error is equal to 49.27, and mean sum of square to the rows, which is equal to sum of square of batches divided by p minus 1, and mean sum of square of batches, which is coming out to be 0.766. Mean sum of square to the treatment can be derived by the formula sum of square of formulation divided by p minus 1, and mean sum of square, which is coming out to be 0.288. Mean sum of square to the block, which is derived by using the formula sum of square of operations divided by p minus 1, so which is coming out to be 12.70 divided by 5, and which is equal to 2.54. mean sum of square to the error, which is equal to sum of square of error divided by p minus 1 into p minus 2, and which is equal to 49.27 divided by 5 into 4, which is equal to 2.46. The test statistics to test the quality of treatment, which is f naught, and after putting in the value of mean sum of square of treatment divided by mean sum of square of error, so we get the result at 0.117, and the f tabulated value at 5% level of significance that can be seen from the table, which is coming out to be 4.56. So the analysis of variance table for the LSD for the swing machine formulation formula. So from the table we can see that the f is evaluated as 0.117, and other derivations are represented in the various columns and rows and in particular cells. So to make a decision about the hypothesis, we have to compare the value of the f statistics with the tabulated value of the f distribution. If the value of the test statistics is greater than the tabulated value at 5% level of significance, then we reject our null hypothesis, that is there is significant difference between the means of treatment. Otherwise we do not reject our null hypothesis and conclude that there is a significant difference in the mean values of the treatment. Here we can see that f tabulated value, which is equal to 4.56, and it is coming up to more than 0.117. So we can say that there is no significant difference in the treatment generated by the combination of operators and raw materials. In the end, I would like to conclude this module. In this module we discuss two major models. One is randomized block design and Latin scale design. In randomized block design, we consider one nuisance factor. So basically it is an extension of the previous module, that is CRD. And in the LSD, we consider two nuisance factor and how to find out the f statistics by using two nuisance factor in the model. So hope you enjoy this module. Thank you.